There we go. Now we're recording. Okay, we good now. So we're going to do a quick review about the banana in the ocean analogy here, all right? And we need to understand, all right, the distribution of the substances that we're going to be talking quite a bit about, right? Because you're going to hear me so many times say sodium. You're going to hear me say so many times potassium. So it's really important, all right, that we know, all right, when the cell is at rest, nothing is going on, right? Like when you're sleeping at night, okay? Your sciatic nerve is doing nothing unless you have restless leg syndrome, all right? But when it's doing nothing, where is everybody, all right? We got to do a roll call. We got to find out where stuff is, okay? So when we're dealing with our cell, all right, inside our cell we have potassium, and that's a cation. It's positively charged. Right, but we also have proteins, that'll be pro, and those are negatively charged. Also inside the cell, right, we've got phosphate, all right, that is also negatively charged, okay? Overall, and I haven't really mentioned this to you, when we talk about the plasma membrane, this blue line is representing the plasma membrane, okay? This is the outside of the cell, and this will be the inside of the cell. So overall, when the cell is at rest, the outside of the plasma membrane is positively charged, and the inside of the plasma membrane is negatively charged, right? So keep that in mind. The neuron's at rest, okay? It's in its resting state, nothing's going on. Inside the cell is negative, outside the cell is positive, okay? So we're talking about the inside, we're talking about the cytosol, what's in that cell. So, majority of the negative charge for the inside of the cell comes from the phosphate ions and the proteins. Even though, all right, potassium is a cation, it's positively charged, all right, but it's outnumbered. So when we add everything up, the inside of the cell is still going to be negatively charged. And when we go to the outside of the cell, all right, in the interstitial fluid, that's where we have our sodium, okay? We've got a lot of sodium, okay? And we also have our chloride. So sodium is a cation, chloride is an anion, okay? But again, there's more sodium outside the cell than there is chloride. There's more positives outside the cell than negatives. So essentially, the outside of the cell is going to be positive, okay? So it's really important. That's why the first bullet point on this slide says it's essential for neuron function. It's important that you understand this distribution, okay? So resting cell, sodium chloride outside the cell, right? Potassium and the negative proteins and phosphate ions are inside the cell, okay? So to help you with that, think of banana floating in the ocean, okay? So that's when the cell is at rest. So the distribution of these materials in the cell and out of the cell help to set up this term here, what we call a membrane potential, okay? And that membrane potential is this down here I was explaining. The outside of the cell is positive, the inside of the cell is negative. We'll get into more details about that. Okay, good so far? That was just a quick review. Unfortunately, that's just straight up memorization, okay? Now we're going to start to see the movement of some of these substances across the plasma membrane. Remember, we've got sodium and potassium leak channels throughout the whole neuron, okay? So there's no gates on those channels. So those are passive channels, which means you're going to get diffusion. And if you recall what diffusion is, it's movement from an area of high concentration to low concentration. Okay? And while that's going on simultaneously, this is all happening when the cell's at rest and it's not doing anything. While that's going on simultaneously, you've got the sodium-potassium ion pump pumping both sodium and potassium against its concentration gradient or up its concentration gradient. That's an energy requiring process. That's an active process. Well, this is what I mean. Okay? So here's our plasma membrane. You've got a leak channel here, okay? And let's just say this is a potassium leak channel because there's way more potassium leak channels than there are sodium. Okay? So we have more sodium. Let's say we have 10 molecules of sodium inside the cell and only 1 molecule outside the cell. Okay? So what we know about diffusion, where's sodium going to want to go? Right, to the outside. I should differentiate. This is the outside of the cell. This is the inside of the cell, O and I. Okay? So it's going to want to go this direction, right? From an area of high concentration to low concentration. And that's what we get. Okay, so it's going to constantly leak out of the cell. It'll only stop leaking out of the cell when we reach equilibrium. Guess what? We're not going to reach equilibrium, all right, normally, because don't forget, we've got that sodium-potassium ion pump. And that sodium-potassium ion, right, I'm not going to even try to draw it, right, but the sodium-potassium ion pump pushes pushes potassium into the cell. So it's going to go from an area of low concentration, there's only 1 sodium, or excuse me, golly, I gotta stop doing that. There's only 1 potassium, to an area where there's a lot of potassium. That's what we're talking about, right? So my point being is I wanted to tell you all that because you're seeing a movement of things, okay? And when you get molecules in motion, you generate energy, okay? It's called kinetic energy is being created, okay? So we're going to talk about a term, it's called the electrical chemical gradient, okay? And that's what helps to determine what we call our membrane potential, that charge across the membrane, that it's positive outside and negative inside. We're going to learn about that now. What makes it positive outside? What makes it negative inside? So we're going to talk about the first part, which is called the electrical gradient, okay? So this is easy. We're dealing with electricity. Okay, we're going to deal with positives and negatives. Okay? So we're going to see with the electrical gradient, right, a positive charge on one side of the plasma membrane and a negative charge on the other side of the plasma membrane. Okay? So that's what this is referring to, that diagram that I showed you, this line with the positive outside and a negative inside. Okay? So because of the distribution that we saw on that previous slide there, we have all that sodium outside the cell, okay? And we have some chloride out there, and we have that potassium on the inside of the cell, but all those negative proteins and those negative phosphates, all right, that's what's going to give us the negative on the inside, right, and the positive on the outside, that distribution on the previous slide. So that's why, boom, that's why you have to know this. Okay? You need to know this distribution because that explains then why, all right, the inside of the cell is negative and the outside of the cell is positive. So this term right here is huge. You heard me talking about it, now you know what that means. The membrane potential is described as the difference in the charge across the plasma membrane. The fact that the outside of the cell is is positive, and that the inside of the cell is negative. Okay? And that's because of all those substances, those molecules that are inside the cell and outside the cell. Okay? So when we talk about an electrical gradient, just like a concentration gradient, remember you'll have more of one thing on one side of the plasma membrane and less on the other. There's a difference, okay? More of something and then less of something. There's that difference. Well, the same thing, we talk about an electrical gradient, but this time we're still dealing with the difference, but it's a difference in the electrical charge. And that difference is the outside of the cell is positive, the inside of the cell is negative. Okay? All right. So this can change because that stuff, those molecules inside the cell and outside the cell can move across the plasma membrane. Don't forget, you got sodium leak channels, you got potassium leak channels. They're going to be leaking, they're going to be moving. Okay? So we can alter and at the same time, we can create an electrical charge. We can make it more negative inside the cell, or we can flip it to where we can make the outside of the cell negative and the inside of the cell positive. Okay? How we do that? One way, we can let a lot of sodium into the cell because sodium is a cation. It's positively charged. Okay? And when we do that, all right, you're leaving chloride outside the cell all by itself. Well, guess what? It's negative. Well, that's one way that we can flip it. Okay? We just need to change, right, the distribution of those molecules. Okay? That's the electrical gradient. I'll get into more detail about that, but you just want to understand. Right now, right, make that all disappear. Know this and this. Okay? The difference in the charge is called a membrane potential, and that's due to the inside of the cell being negative, the outside of the cell being positive. And it's positive and negative because of what you saw on the previous page. Okay, cool? All right. So we'll go here to the chemical portion, the chemical concentration gradient. Remember, this is an electrochemical gradient, what we refer to it as. Okay? And what this has to do with, this is much easier. Okay? This has to do with the unequal distribution between the two areas. Well, what areas are we talking about? We're talking about inside the cell and outside the cell again. Okay? So this has to do with that distribution slide that I showed you. Okay? We're talking about specific chemicals. The fact that we see more more potassium on the inside of the cell, all right, helps to contribute, all right, to the overall charge both inside and outside the cell. Meaning, let me start with the easier one. Sodium, right, in higher concentration outside the cell. Sodium is a cation, so it makes the outside of the cell more positive. Granted, there's more sodium on the inside of the cell, okay? So, but there's still far more negatively charged proteins and negatively charged phosphate ions in there, okay? When we're talking about the chemical concentration gradient, we're specifically talking about, all right, those chemical substances on that distribution slide, okay? Where is chloride? Where is sodium? Where is potassium? Okay, where are all those things? Right? When we're talking about the electrical gradient, yes, we're talking about the distribution of those substances, but we're talking more about the charges of those substances. What's negative, what's positive. Okay? So that brings us to this part here, all right, when we're talking about electrical currents. Okay? So going back to chapter 2, you know that a charged particle, all right, is an ion. So sodium is an ion. Calcium is an ion. Potassium is an ion. Chloride's an ion. I could go on and on, right? But that's what we're going to discuss. So we've heard this term here, the membrane potential, right? You need to know this definition. I cannot stress it enough. It's going to be that difference in the charge distribution across or at the plasma membrane. If you want to make it simple, okay, that the fact the outside of the membrane is positive and the inside of the membrane is negative. Okay? Is anyone here taking a physics class? Okay. All right. It's okay if you didn't. I took a physics class a long, long time ago. And I had to learn how to build circuits and all that fun stuff. So you learn about resistance, amperage, and voltage and all that. Okay? So since we are dealing with electricity here, all right, we'll, whoops, get rid of that. That's since junior year of high school. Well, yeah, I took it in junior year in was it junior year or senior year? Anyways, I took it in high school. I took chemistry junior year. So senior year I took physics. Anyways, we did more like Newtonian physics. Object in motion tends to stay in motion, blah, 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 you know. So when I was in college, that's when we did the circuitry stuff. The point being is, we're dealing with an electrical charge, okay? And we're dealing with the circuit. Right? Electricity is going to experience resistance. And in this case, the plasma membrane is going to be the resistance that the electrical charge that travels down a neuron. That's what's going to slow down and decrease the amplitude or the power of the electrical charge, the nerve signal. Okay? So when we talk about the resistance, we're going to think the plasma membrane. Okay? The plasma membrane is a selectively all right, permeable barrier. Remember that before? It lets certain things out, certain things in, okay? But the same thing. It's going to allow, all right, certain ions in and out, all right? The leak channels, perfect example, okay? But the plasma membrane itself, right, will only let things that are very small and non-polar, okay, cross the plasma membrane itself. That can go right through the phospholipid bilayer. Well, guess what? Ions are charged, okay? So they cannot cross. They have to go through a channel, all right? So this is what we're talking about with the resistance here of the plasma membrane. So a good way to decrease the resistance to let those charged particles in, okay, is to put more channels in there. If you put more, simple, if you're in a rowboat and you start punching more holes into it, will you not get more water entering the boat? Same thing here. If you want to decrease the resistance and increase the amount of those sodium and potassium ions coming into the cell or leaving the cell, all you have to do is open up more channels or put more channels in, okay? And that's what we're talking about. You want to increase the resistance and you close the channels, because then they can't get in. It's like zombies knocking on the door, close all the doors, they can't get in. You want the zombies in the house, open up the doors, let them in, okay? All right. So this last bullet point here talks about briefly what I was mentioning when we were talking kinetic energy. When you get charged particles, charged ions, okay, like sodium and potassium, when sodium and potassium are moving through those open channels there, okay, when they're moving, they are going to create a current, okay? Current is usually measured in amps, right? But you will create, once sodium is leaking into the cell, once potassium is leaking out of the cell, you're going to create a current, electrical charge, right? That is also going to help with the membrane potential there. I'll get into this in much more detail, y'all. I'm just kind of throwing some basic stuff at you here. So, all right, first of all, let's figure out what an electrical gradient is. Okay? You need to know this definition here. Right? It is the difference between the electrical charge between two areas. In our case, we're dealing with the inside of the cell is negative, the outside of the cell is positive. Okay? Keep it. When we're dealing with the chemical gradient, we're talking about the unequal distribution of a substance between two areas. And going back to the cell again. Okay? You have 140 molecules of sodium outside the cell and about 40 molecules of sodium inside the cell. So that creates our chemical gradient. We have more outside than inside. Okay? So together, we call that an electrochemical gradient. All right, so let's start off in the basics with the neuron. Okay? You got a neuron. We're going to start here. Okay? This is going to kind of explain some things to you. There's a lot of information on the slide, so I'm going to kind of take it easy and go slow. Okay? All right. So when we're dealing with our neuron at rest, okay, remember we have, right, our potassium inside the cell. It never, and then we have our negatively charged proteins and negatively charged phosphates. They never leave the cell. They're always in there. They can't leave. Okay? The only thing that can leave the inside of the cell for our purposes right now is the potassium. Okay? Then on the outside of the cell, we have our sodium, right? And we have our chloride. And when we get down to the distal end or the terminal end of the neuron, we'll start talking about the calcium. Okay? For right now, let's not worry about that too much. Okay? So when the cell is at rest, okay, that is our normal distribution. Potassium inside, sodium chloride outside, banana in the ocean. Okay? But what maintains this chemical gradient are those pumps and leak channels. Okay, they're maintaining to make sure that sodium stays outside the cell. And at the same time, they're maintaining that potassium stays inside the cell. So that's what happens. We have a higher concentration of potassium in the cytosol and a higher concentration of sodium and chloride in the interstitial fluid. Okay? Keep that in mind. All right. Also, when these neurons are at rest, all right, the gated channels are going to be closed. So our remember all those gated channels that we learned about? Chemically gated channels, voltage gated channels, okay? Those are all closed. We're not doing anything, okay? We're not doing anything. All right. So because of that distribution, and because of the operation of those leak channels and the sodium-potassium ion pumps at a neuron at rest, right, we generate an electrical charge, okay? And we call that a membrane potential. All right, I'm going to read this part to you. Cytosol is relatively negative. We knew that, mainly because of the phosphate molecules and the proteins, right? They can't leave, but they are negatively charged, okay? So what we did, does this have a picture of it? Nope. I don't think I put it in here. Kind of. What we did is we took this voltmeter here and we stuck, all right, one of the electrodes on the outside of the cell, then we took another one, we stuck it on the inside of the cell. What we did is we measured the electrical charge in a resting neuron across the plasma membrane. And that value, which you definitely need to know because you will be asked this, is a negative 70 millivolts. Commit that to memory. That will be a test question for most of you. I can't say for everybody. I always put it on a test. Okay? And so that we give that a name, the resting membrane potential. So what does that mean? That means that is the membrane potential, the difference in the electrical charge across the plasma membrane when the neuron is at rest, when it's doing nothing. Okay? When it's doing nothing, right, all of those channels, the gated channels, are closed. Okay? And then sodium, potassium leak channels are leaking stuff in and out, right? And the sodium potassium ion pump is moving sodium out of the cell and moving potassium into the cell. Okay? All right, good so far. At least tell me that you know this. Resting membrane potential, negative 70 millivolts. Know that. Okay? And then you just got to remember that a membrane potential is going to be the difference in charge across the plasma membrane. Right? That's what this is. Electrical charge difference across the membrane. Okay? That is referred to as the membrane potential. So the resting membrane potential is that difference in charge when the neuron's at rest, not doing anything. Okay? All right. So let's get into a little bit more detail of what's happening with the resting membrane potential. Specifically, I'm going to talk about, this whole slide talks about potassium. It's a lot, all right? But you need to know this. First of all, this is another great test question. Potassium is the most important factor in setting the resting membrane potential. The reason why, okay, the negatively charged proteins and the negatively charged phosphate ions cannot leave the inside of the cell, but potassium can. So if it leaves the inside of the cell, it makes the inside of the cell more negative, okay? Because remember, potassium is positive, so it takes its positive charge with it, okay? So if more potassium enters into the cell, it makes the inside of the cell less negative. But you have to, and I'll get to the whole reason. I'm jumping off onto a tangent here, okay? So potassium always wants to leave the cell. Why? Why does potassium want to leave the cell? Booyah, perfect, yes. Concentration gradient. Remember, there's always more potassium in the cell than outside the cell. All right, and we have a leak channel there, so it wants to go down its concentration gradient, and it wants to leave the cell. It wants to move out, diffuse. When you see this word diffuse, that's a passive process. We're always going to move down our concentration gradient. It requires no energy. Okay? Okay, so here's an interesting fact. So as potassium and its positive charge are diffusing out of the cell, the inside of the cell becomes more negative. Okay? So what do we know about opposites? North pole, south pole, what do? On magnets. North pole, south pole. Opposites attract, right? Same thing with opposite charges. Negative charges and positive charges attract each other, okay? That's how we're dealing with when we were talking about ionic bonding and covalent bonding, guys. Right? So opposites attract each other, right? So as the inside of that cell becomes more negative because the potassium keeps diffusing out, it keeps leaving, all right? That difference in charge becomes bigger. So the negative charge is going to want to pull on that positive charge. So it's going to start to resist all that potassium leaving. In the beginning, there's so much potassium there, it just flows out. But as less and less and less are left behind, and that difference between the positive and negative charge becomes greater, so it becomes stronger. So it pulls that potassium. It starts, I won't say it starts to pull it back in, but it makes it much more difficult for it to leave. So that's what we're talking about here. It's limited by the electrical gradient here, okay? So as more potassium diffuses out, this electrical gradient becomes bigger, because remember, we still have those negative charge structures inside the cell, right? And so they're going to pull on that remaining amount of potassium. So it makes it harder for that to leak out, okay? This symbol here is inorganic phosphate. That's what that means, okay? So eventually, we'll get to equilibrium, right? And what that is when the chemical concentration gradient is equal to the electrical concentration gradient. Meaning, you know, as more and more potassium leaks out, okay, that electrical gradient will get stronger. Eventually, it'll stop that potassium from leaking out. And so they'll both the chemical and the electrical gradient difference will stop movement altogether. So we'll reach that equilibrium. We won't see any more movement of potassium. Okay? All right. So you heard me, I was going to say last week, you heard me say last week, all right, that there are more potassium leak channels than there are sodium leak channels. Okay? We have a heck of a lot more potassium leaking out of the cell than sodium leaking in. Okay? If we were to get rid of all the sodium leak channels, we'd be done with that. So the only leak channels that we had in existence were potassium. Okay? So if only potassium could leave the cell and nothing could come in at a resting membrane, right? Then our normal, okay, resting membrane value potential would be -70. Okay? So if only, right, potassium was to be allowed to leave, okay, when your electrical and chemical gradients reach equilibrium, that value would be -90. But since we have sodium present, right, or sodium leak channels present, right, then our value is -70. Okay, so just keep that in mind. Equilibrium is established with sodium and potassium leak channels at -70, but if we didn't have any sodium leak channels and we only had potassium leak channels, then equilibrium would be reached at -90. Okay. And that's what I think this next slide talks about here. Oh, no. Okay. No. This talks about sodium's role. Sodium doesn't play as much of a role, right? Mainly because there's fewer leak channels, right? But it does influence the resting membrane potential. Because remember, right, sodium is going to leak into the cell. And remember, it'll bring in its positive charge. So as it brings in its positive charge, here's the thing. Remember, it's negatively charged inside, right? Opposites attract, right? So if sodium is positively charged, will it not be drawn into the cell? Won't it want to move into the cell? And it's also got its concentration gradient. There's more sodium outside the cell and less inside the cell. So when it's leak channel, it's going to go down its concentration gradient into the cell, but also you've got the electrical gradient. It's positive outside, but negative inside. So it's going to be attracted to that negative charge. So it's going to move down. So it's going to move down the concentration gradient, and it's also going to be pulled into the cell by the electrical gradient. Okay? But because of our leak channels, right now our resting membrane potential is that -7. Okay? Seen this asked as a test question before, this concept. Okay? If you only have, right, potassium leak channels, what would the resting membrane potential be? -90. Okay? So the walk-away point from that is that potassium leak channels influence the resting membrane potential way more than the sodium leak channels do. Okay? They influence it a little bit, but it's mainly the potassium leak channels. Okay? All right. So we learned about the sodium leak channel, we learned about the potassium leak channels. We learned about the sodium leak channels. But what's the role of the sodium-potassium ion pumps on our resting membrane potential? Okay? So keep in mind, right? Every time the sodium ion pump, right, does a pumping maneuver, it's going to pump out of the cell 3 sodium ions, and it's going to pump into the cell 2 potassium ions. Okay? So basically, all right, it won't make all that much of an effect on the resting membrane potential. Okay? In regards to the electrical gradient, because it's pumping 2 positively charged ions. It just happens to be pumping out of the cell 3 positives and only pumping into the cell 2 positives. Okay? That's only going to affect it by about a -3 millivolts. That's not terribly important. Right? This is important. It plays a small role in establishing the resting membrane potential. Potassium leak channels that do the major role. And then it's going to be the sodium leak channels. Then it's this pump. But what it does do, right, is that it maintains that concentration gradient. That's what you really need to know. Remember, sodium wants to enter, potassium wants to leave, right? But this pump is that guy that's bailing water out of the rowboat, okay? Right? As the water's leaking in, this guy's bailing it out. So as sodium's leaking in, this pump's bailing it back out of the cell. And as potassium, all right, is leaking out, it's putting it back in, okay? So it's doing this 24/7, all the time, all right? And in fact, I said this before, it makes up 2/3 or 66% of the energy expenditure. Okay? It costs 1 ATP to pump 3 sodium out of the cell and 2 potassium into the cell. Okay? It's going on all the time. Okay? So think of it that it's more of its importance in this role of maintaining the concentration gradient. It's maintaining, right, the banana floating in the ocean. Okay? That's its job. It's to keep potassium in the cell, sodium out of the cell. Chloride. Well, chloride doesn't have anything to do with it. Okay? So this is what we're seeing here. This is all working in concert with one another. Okay? We're seeing, right, put it into picture perspective, right? Here's your sodium-potassium ion pump, moving sodium out of the cell, putting potassium into the cell. Meanwhile, potassium is leaking out. Meanwhile, sodium is leaking in. The whole time, negatively charged protein can't leave. It's too big, can't go across the plasma membrane. And our inorganic phosphate, it can't leave either, and that's negative. Okay? So you can see all this is occurring simultaneously. And all that goes on in a resting neuron, and that's what generates that membrane potential, that charge across the plasma membrane, that negative 70 millivolts, the fact that it's more positive outside the cell than inside the cell, okay? So now, what do we want to do? We want to change that resting membrane potential now, okay? We are going to change this number. We're going to go from a negative 70 maybe to a negative 60 or a negative 50, or we get really extreme and take it up to a positive 30. And we're going to talk about all that, right? So just keep that in mind. Okay? It's really important. That's why you probably have to go back and watch, all right, the video here, that you understand all the roles here that are played, right, in generating that resting membrane potential there. All right, the resting membrane potential is primarily established by what two structures embedded in the plasma membrane? All right, we got sodium, all right, leak channels and potassium leak channels. Which of these two plays a bigger role? Potassium. Yep, potassium plays the major role. Okay, that's what's going to establish our resting membrane potential. Of what value? Negative 70 millivolts. Okay, negative 70. Burn that into your brain. If you don't want, if nothing else that you walk out of here today with, walk out of here with negative 70 millivolts. All right, and I'll be happy. Okay, we're going to go over a couple terms here. Okay, so we now kind of know, right, how we establish that resting membrane potential. Functions of the leak channels, the functions of the pump, what happens when those molecules start to move in and out of the plasma membrane, how it creates that electrical difference in charge across the plasma membrane. We also know how the chemical concentration is different across that plasma membrane because of the operation of those pumps and channels. Right? So we now assign some terms to what is happening. Okay, so we have depolarization and hyperpolarization. Okay, so now what we're going to do is we are, all right, like the title of this slide says, we are going to change that membrane potential. We are going to change that negative 70 millivolt value. Okay, and to do that, all right, because we really aren't going to affect the leak channels, we're not going to affect the sodium potassium ion pump. That's going on at the same time that all this is going to be going on. Okay, so in order to change that membrane potential, we're going to open up some of those other gates that we talked about. Okay, we're going to open up some of those chemically gated channels, and we're going to open up, or I should say, we're going to open up some of those voltage gated channels. Okay, and those gated channels will now influence, all right, that membrane potential, that resting membrane potential, because what they'll do is, depending on what channel we open up, it's going to allow a specific ion to flow through. Because remember, these channels are ion specific. You can't have sodium travel through a potassium channel. Okay, that's one thing you definitely need to know. Okay? It's not like when you drain your tub that it drains the water, the soap, and all the other garbage that's in the tub in the tub water. All right, this is specific. Okay, so it's only specific to a specific amount, a specific type of ion here. And when that ion either enters the cell or leaves the cell, it's going to change your resting membrane potential. Okay, all right. So the first term that we're going to discuss is depolarization. This happens at the plasma membrane. So you got to commit this one to memory, folks. This is what happens when the inside of the cell becomes more positive. Okay? Or you could say this is what happens when the inside of the cell becomes less negative. Okay? Because if I go from a negative 70 millivolts to a negative 60 millivolts, is that becoming more positive? Negative 70, negative 60, 50, negative 40, 30, negative 20, negative 10, 0, plus 10, okay? So when I go from a negative 70 to a negative 60, I'm becoming more positive, or you could say less negative. Either or. I'm just going to stick with the definition that the book uses, more positive. Okay? Like this example. going from -70 to -60. Okay, so to do that, we're going to open up a channel, a gated channel. Okay, it can be chemical, it can be voltage gated, regardless. All right, but we need a stimulus, and that stimulus has to cause that channel to open up. Right, and when it does, we call that reaching the threshold. Right? And we'll talk about what that threshold is. Okay. So in depolarization, what we've done is we've opened up a channel, and sodium is going to enter into the neuron. Because sodium is positive or negative? Positive, right? So if sodium is positive, okay, and it enters into the cell, is it making the inside of the cell more positive? Yes, it's making the inside of the cell more positive, okay? That's what happens here. The inside of the cell becomes more positive, and so much sodium will enter in fast, right, that it'll, for a brief moment, get into the positives. It'll become a positive 30 millivolts, okay? Regardless, okay? We've made the inside of the cell more positive. That term is called depolarization. You need to know that. You need to know that because when we talk about, when we get into chapter 10 and we're going to be talking about muscles, very similar phenomenon. I'll be using depolarization, so please commit that to memory right now. Depolarization is the process of making the inside of the cell more positive. Okay? All right. So now you can see here what we're talking about in this picture. So we are going to change the resting membrane potential, all right, into, we're going to depolarize it. Okay? So what we're seeing here is this gated channel, all right, it's a sodium gated channel, it's opened up. Sodium enters in, brings its positive charge with it, and it now makes that resting membrane potential, or that membrane potential, -60. -60 is -60 more positive than -70. Oh, all right, okay, good. Okay, so that's what we're seeing here. All right, sodium flows in for depolarization. Okay, so repolarization, simple, right? This is when we go back to resting membrane potential. So if we're going to repolarize something, same example, we're at -60 now. Now we need to make it -70, okay? So we need to make the inside of the cell more negative, okay? How do we do that, okay? Normally, okay, when we're dealing with resting membrane potential, the voltage-gated potassium channels are closed. Okay, so some sort of stimulus is going to trigger that channel to open up. It'll open up that gate. Okay, and that whatever that stimulus is, all right. If we're dealing with the voltage-gated channels, it's going to be, the stimulus is going to be an electrical charge of some sort. Okay, it's going to be a change in the electrical charge. So if it's enough to open up the gate, we call that threshold value again. There we are talking about that threshold. So we need enough of a stimulus to open that gate. When it does, then that means we've reached its threshold. Okay? So in this situation, I don't know what that was. All right. So in this situation, all right, when we're going to get to repolarization, we have to wait for depolarization to end. So when we reach this value here of positive 30 millivolts, right, then sodium will stop entering the cell. I'm going to get into this again in much more detail. Okay? So when that happens, the sodium channel's closed. No more sodium's coming in. So we cannot get any more positive than this value here right now. So now what we do is we open the potassium channels, and potassium leaves the inside of the cell, and it's going to take its positive charge with it. Right? So when it's leaving the inside of the cell and it's taking its positive charge with it, what's it doing to the inside of the cell? Making it more negative. That's right. Okay? Because the negative charge stuff can't leave. Inorganic phosphate, which is negative, can't leave. Proteins can't leave. They're stuck there, okay? But when the positively charged potassium leaves the inside of the cell, it takes its positive charge with it. It makes the inside more negative, okay? Until it gets to this value here. So the stimulus that we need to reach threshold, all right, is going to be when these voltage-gated sodium channels shut down and close, okay? When they close, we're usually at this value here, that positive 30 millivolts. I'll get into much more detail about that. But what I want you to know is depolarization, make the inside of the cell more positive. Repolarization, you make the inside of the cell more negative. Okay, we're going to try to return back to our resting membrane potential of negative 70 millivolts, okay? All right, there's this last term here. Well, let me show you a picture here real quick. All right, here's the repolarization. You can see here's the resting potential, positive outside, negative inside. Now what we've done is we flipped it. It's more negative outside, okay, and more positive inside. All right, once we reach that positive 30 millivolts. When that happens, then the potassium, the voltage-gated potassium channel opens up. Then all this potassium that's just been hanging out in here leaves. Okay? And as it diffuses out, it takes its positive charge with it, and it starts to make, right, the inside of the cell more negative. It starts to return it back to the negative 70 millivolts. Okay? I'm going to go over this so many more times you're going to get sick of it. Not today, though. All right? I'll get into the specifics of it. Okay, the last term here is called hyperpolarization. Okay? So the definition for hyperpolarization is when we make the inside of the cell even more negative than what the resting membrane potential is. Resting membrane potential is negative 70, so we'll make it negative 80, maybe negative 90. Okay? So we're going past the resting membrane potential. Okay? So keep that in mind. When we talk about something, excuse me, being hyperpolarized, we're talking about, okay, it being even more negative than the resting membrane potential value, which is negative 70. Okay? So this is a result of, all right, the voltage-gated potassium channels being open. It can also be a result of the opening of these guys, chloride channels. Okay, because remember, chloride's on the outside, right? And so if we open up those channels, chloride will want to enter into the cell. It diffuses down its concentration gradient, and it brings its negative charge with it to the inside of the cell, and it makes the inside of the cell more negative. Okay? So eventually, when all this happens, we'll eventually get back to our negative 70 millivolts through the hard work of the sodium-potassium ion pumps. Because temporarily, right, we'll wind up at that negative 90. Okay, so we got to find our way back to the negative 70 millivolts, no problem. The sodium-potassium ion pump is going to pump those ions out of the cell or into the cell. And then that will bring us back down to our resting membrane potential. I'll get into much more detail and specifics on that when we get to the axon. But for right now, just know hyperpolarization is when we make the inside of the cell more negative than the resting membrane potential value. Okay? All right, so that's what we're seeing here. Okay? We have our potassium channel is still open, and it's letting that potassium not leak out, but diffuse out. And then we have our chloride channel open, and that's letting chloride, right, diffuse in. And now we've gone from a negative 70 to negative 80, possibly get up to a negative 90. Okay. So this is what we see, right, when we're talking about hyperpolarization. Potassium is leaving the cell, chloride is entering into the cell. That can hyperpolarize the cell. All right, so how does depolarization occur in a neuron? All right, when we open up a voltage-gated sodium channel, and that's going to allow that positively charged sodium move into the neuron, okay? Or it could be some other cation ion. It doesn't necessarily have to be, but for our purposes, we're going to be using sodium most of the time, okay? Calcium, calcium's another cation ion, so we can depolarize a cell with calcium, okay? Hyperpolarization, right, when we're dealing with, right, the gated potassium channels opening up and potassium diffusing out, and then also with the chloride channels opening up and then chloride diffusing into the cell. And that's when we make the inside of the cell much more negative past the resting membrane. All right. So now what we're going to do, and this is what I was kind of talking to you folks about earlier, about the different segments of the neuron. All right, we're going to start here at the receptive segment, and I'm going to basically tell you a story. All right, how? All right, another neuron, let's say. Okay, here's its teledendra, then it's got its synaptic knob here. Okay, and how it's going to try to create an action potential here in the axon. So we're going to start here. We're going to talk about what happens here, how the dendrite then sends its signal down here to the cell body, and then how the cell body is going to try to get its signal here to the axon hillock, because what happens at the axon hillock? What did I say? Last class. It's hard to see the word here. Yep, it initiates something. What's it going to initiate? Action potential. That's right. Okay? Because our goal is to get an action potential to occur. Action potential is like, you ever set up a row of dominoes? You tap the first domino and it knocks all of them down. That's what an action potential does. It's what we call an all or none phenomenon. Okay, so we're going to set up all these dominoes along the entire length, right, of the axon. And once we hit that first one, they're all going to fall down. Can't stop it. It's just going to happen. Okay, so all we need to do is we need to get our signal, our message to this area here to initiate the action potential. Because once that happens, then we can just sit back and relax, because it's just going to go right on down the axon and then all the way to the synaptic knob at the other end. And we'll talk about what happens there. So that's what we're going to do. We're going to talk about what happens at each of these segments, okay? Kind of give you a little bit more of a better understanding. So to do that, okay, so we're going to start off here in the receptive segment. Okay, remember the receptive segment, okay, is made up of the dendrites and the cell body, the soma. Okay, and the channels that you have there and the pumps that you have there, all right, are going to be your sodium-potassium ion pump, because that's found throughout the entire neuron. Your sodium-potassium leak channels, because that's found throughout the entire neuron. But importantly, we're going to have chemically gated ion channels. Okay? That's going to be what we see, all right, in the receptive segment. All right. So I can't talk about the receptive segment without talking about graded potentials. Okay? So I want you to think of a graded potential as a mini action potential. I hate to use that term. That's the best way to describe it. Okay? What does that mean? They're small. They're not going to be as powerful as an action potential. And they're short-lived. They don't last for a very long time. It's like a sparkler. You ever seen those sparklers on 4th of July? Those things never used to last long enough when I was a kid. But a road flare, that lasts for a long time. All right? So the road flare is like our action potential, and the sparkler is like our graded potential. Okay? So that's what we're going to be looking at here. Okay? So again, what we ultimately are going to try to do is we're going to try to change that resting membrane potential. Okay? All right. So, like I said, when we're in the receptive segment, we're going to be dealing with these chemically gated ion channels. So that means if we're dealing with a chemically gated channel, that means we're going to be dealing with neurotransmitters. Those are going to be the chemicals that are going to open up those chemically gated ion channels. Good so far? All right. Right. I know this is a lot. This is definitely going to be one of those videos that you're going to be watching again. I can tell you that right now. Okay? All right. So this is what's going to happen. All right? In the receptive segment, our goal is to open up those chemically gated ion channels so we can let ions into the cell. We just learned about depolarization, hyperpolarization, and repolarization. So now we're going to put those terms into play here, okay? So what we need to do is we're going to try to generate what we call a graded potential, okay? So those are going to be these small local currents that don't last for a very long time, okay? So let's talk about a little bit about some of these graded potentials, right? So when we're discussing the graded potentials, we're going to discuss, all right, the two terms, depolarization and hyperpolarization. So a graded potential can be very small or it can be large, but what that means is large for a graded potential. A graded potential is not going to be as massive as an action, okay? It's like having all the, like you got, what is it, Jupiter that has like 19 moons or 16 moons or whatever, right? You got the planet, and that's the action potential. Then you got the little moons orbiting around it. That's like the graded potentials. But yet some moons are bigger than others, and some are smaller than others, okay? So these graded potentials can be relatively large, and it all has to do with the number of gates that we open up. So the more gates we open up, the larger the graded potential, right? The fewer gates we open up, the smaller the graded potential is going to be, okay? But what we're going to do is certain graded potentials are going to depolarize the cell. So what does that mean? You're going to make the cell, the inside of the cell, resting membrane potential, which is -70, you're going to make it more positive. So we're going to take it to maybe -65, okay? Other types of graded potentials are going to hyperpolarize the cell, okay? So they're going to go and take the resting membrane potential from that -70, and they might make it -75, okay? So they'll make it even harder in order to get an action potential, okay? And we'll get into those different types, okay? So keep that in mind. That's what this statement here says. They vary in degree of change and direction of change of the resting membrane potential, meaning it can make the plasma membrane less negative, which is saying it can make it more positive. That's what depolarization is. Or it can make it more negative. That's what hyperpolarization is. Okay? So these graded potentials can do one or the other. Okay? One of the things that you have to understand is they move parallel to the plasma membrane. Simple. Here's the plasma membrane. The graded potential moves right along it. Okay? Here's the problem. Think of a graded potential like throwing a rock into a very calm lake or a pond. Right where you throw it in, the ripples are big. But as they travel further and further out, they become less and less. Why is that? Right? The energy, if you're into, again, this gets into physics, the wave energy that's generated, right, that travels through the water, it becomes weaker and weaker as it moves away, simply because of the resistance it encounters in the water. Right? Same thing happens with graded potentials. They encounter resistance from the cytosol. Right? That's water. There's fluid in there. All right. Remember, cytosol is more viscous than water. It's like a kind of gooey. All right. What would you rather swim through, water or Jello? Right? I'm not saying that's what the cytosol is. It's not Jello, but it's more viscous, right, than water. Okay. So that's what we're talking about. Graded potentials are going to experience resistance from all the stuff that's found in the cytosol. Okay, so it'll become weaker and weaker, just like when you threw that rock into the pond. Right, as the ripples got further and further away from where you threw the rock in, they became weaker and weaker and weaker, and then eventually went away. That's what's going to happen to a graded potential. That's why they're short-lived, right? And they're local. They don't travel throughout the whole neuron. They're only found in the dendrite and also in the cell body. I've always wanted to swim in a pool full of Jello, pudding. I don't know why. Jello seems too thick to me. I'd like. I saw that. It's the same one I'm thinking of. Like, well, since we're talking about Jello, who is it? It was Bill Cosby that used to do the Jello pudding pops. Yep. But I don't. Yeah, let's not talk about that. All right, here we go. Let's get into the receptive segment here. All right. So staying on the receptive segment, we're going to talk about the graded potentials. All right. And remember that, well, I didn't, it's gone now. There's not much room for me to draw here. Good, I'm just going to use the whiteboard. All right. So here's my horrible drawing for the one neuron. Okay, we're going to deal with two neurons here. Here's a dendrite, here's another dendrite, here's another dendrite, here's another dendrite. So we've got our other axon from this other neuron coming in, and then it has its teledendra here. Okay, so one teledendra synapses here. Right, another teledendra can synapse right onto the cell body. Another one can go over to this dendrite here. And this one can go over here. Right, the point being is, remember we talked about synapses, right? Where a neuron contacts either another neuron or an effector, which is muscle or gland. Okay, so this is our presynaptic neuron. This one over here is our postsynaptic neuron. Okay, so now we're going to talk about when an action potential travels down from another neuron, it travels down here to the synaptic knob, and then what happens in this area here. Okay, and we're trying to generate a graded potential. Remember, the responsibility or the function for the dendrite is to essentially send any type of signal to the cell body. Then its job is done. Then the cell body takes over and it'll transmit that signal, hopefully, to the axon hillock. Okay, so we're going to talk about all that here. How do I get back to the other thing? Oh man. Was on 50? All right. We only have 150. You break it, no, you break it, you buy it. Don't worry, we only have 150 more slides to go. We'll be good. I'm kidding. I'm joking. This slideshow used to be close to 200 slides, so it's not like that anymore. All right? I fixed it. I got rid of stuff. All right. Yeah, no, trust me. I used to cry too having to teach it. Anyways, so that's what we're talking about when we're dealing with the graded potentials. Right? We're going to be dealing with the postsynaptic neuron. So we give them a special name. We call those postsynaptic potentials. So this is where you have to memorize this stuff. Right? A postsynaptic potential that will depolarize, right, the neuron. I shouldn't say the neuron, which will depolarize the plasma membrane, right, in the cell body, is referred to as an excitatory postsynaptic potential, or I'll call it an EPSP. Okay? Depolarization creates EPSPs. Right? Hyperpolarization, when we make the inside of the cell more negative, okay, we call that an inhibitory postsynaptic potential, or an IPSP. Okay? So EPSPs will depolarize the cell. They'll make the cell, the inside of the cell, less negative. So we'll go from our negative 70, right, to negative 60. Okay, that's what an excitatory or EPSP will do. Inhibitory will make the inside of the cell more negative. So we go from a negative 70, and then we go to like negative 80. Okay. So keep this in mind. Neurons have tons of other neurons that synapsing on top of it, okay? And some of those neurons will be creating and generating EPSPs. Some of those other neurons will be generating IPSPs, right, in the postsynaptic neuron. Okay? So a lot of this stuff, it's not just one synaptic knob doing all this. You could have hundreds, thousands that are going to be doing. That's what we talk about. These postsynaptic potentials are quite numerous because you have numerous neurons synapsing on our postsynaptic neuron. I think I got a picture of one. I do. There you go. Here you can see it. Right? Here's the cell body of our presynaptic neuron, the purple. You can see all these synaptic knobs from all these different neurons, right, that are synapsing on this one presynaptic neuron. Okay, here's an example. All right, this drawing. You see this one right, postsynaptic neuron, and then all these synaptic knobs coming from a bunch of different neurons. So that's what's going on here, right? That's what we're talking about, that a lot of this stuff can be occurring simultaneously. Where am I? Here. All right, actually, I'm here. Okay, so this is story time. I'm telling you, story time. I'm going to go back and forth and show you pictures, okay, between this and the between EPSPs and IPSPs. But let's start off here. Right? How do we make an EPSP? Because remember, when you see EPSP or an excitatory postsynaptic potential, your first thought should be depolarization. Okay? Depolarization, which means we're going to make the inside of the cell less negative or more positive, right? Agreed? Okay. So here's what happens. Okay? You've got our neurotransmitter, okay, in the presynaptic neuron. Okay? It gets released from that presynaptic neuron. It diffuses across the synaptic cleft, right? It's going to bind onto the receptor on the postsynaptic neuron that's attached to one of our chemically gated channels, okay? When it finds that receptor and it binds to it, that's the stimulus that's going to open up that chemically gated channel. That chemically gated channel is going to let a specific type of cation, right, move either into the cell or out of the cell. So let me show you the picture here. Come back so you know what the heck I'm talking about. What's that man saying? Don't worry, I'll show you. All right, here you can see, here's our presynaptic neuron. All right, all these different presynaptic neurons synapsing onto our postsynaptic neuron. That's what we're seeing here. So, all right, our presynaptic neurons, they're releasing their neurotransmitter, okay? That neurotransmitter diffuses across the synaptic cleft here, and it finds a receptor on these gates here, okay? It finds the receptor, it binds to the receptor, and that receptor now, right, stimulates the opening of the gate. So a cation, in this case, sodium, because we know where is sodium in abundance? Where do we find more sodium? Outside of the cell. So once we open that channel, sodium moves into the cell, right? Or at the same time, okay, will also cause, right, potassium to leak, not leak, excuse me, right? Will cause potassium to diffuse out of the cell. Regardless, right? If positive, right, sodium ions are moving into the cell, okay, and very little, all right, potassium is leaving the cell, okay, you're still going to get more potassium or sodium moving in. What are we doing to the inside of the cell? Charge-wise, sodium's positive. We're making it more positive, right? Okay, we're going to make it more positive. So in this example here, all right, as sodium moves into the neuron, okay, we go from that -70 to a -68. Not a lot, but still, that's good. We're getting there, all right? I haven't told you folks this, and I should probably tell you, all right? My real name is, no. What I need to tell you is, all right, the threshold value. All right, I haven't mentioned this. Let me go back to the previous slide here. The threshold value is this value that we need to achieve, a numerical value of -55 millivolts. You need to write that down, okay? Threshold value of -55 millivolts. When we reach that value, ideally we need to reach that value at the axon hillock. If we reach that value, that's then, when we get to -55 millivolts, that's when we generate an action potential. Okay? That value has to be achieved at the axon hillock, at the initial segment, right? You don't reach that value at the axon hillock. If it's -56, hey, great try. That's what we call sub-threshold value. We almost made it there, but we weren't quite there. We have to get to -55. And that happens, bam, and we push down that first domino, and we get our action potential. Okay? So that's step one. Okay, the neurotransmitter diffuses across the cleft. It opens up the chemically gated ion channel. What do we see? Sodium floods into the cell. Some potassium leaves, all right, but it doesn't leave as quickly as sodium enters in. So the inside of the cell becomes more positive. It goes from that -70 to -68. Okay, and so that whole process we refer to as that EPSP, that excitatory postsynaptic potential. Okay, but again, unfortunately, when this occurs, all right, it experiences our little potential guy here, all right, our EPSP. Again, its goal is to move towards the initial segment. That's where it's going. Got a job to do. Got to get to that initial segment, and it's got to get that -55 threshold value achieved at the initial segment. But unfortunately, as it moves across the plasma membrane, it's going to experience resistance from the cytosol, so it becomes weaker, weaker, and weaker. Okay, and it can die out. It just depends on how big it is. That's what we're seeing here. Okay, here's your resting membrane potential. This is our graph. Time, all right, we got our membrane potential, so our voltage over time. So you can see here, everything's good, all right, -70 resting membrane potential. Bam, a stimulus occurs. The stimulus is the neurotransmitter. It's released onto the chemically gated ion channels, all right? They open up, okay? Sodium rushes in. That's this little blip here. Okay, so it goes from -70 to -68. But as it's traveling across the cell body, it becomes weaker and weaker because it's experiencing resistance and it dies off. We need to get to this value here, this threshold value, at -55, okay? And we need to get to that -55 value at the initial segment. We'll talk about how we do that, okay? All right. Here. Okay. So unfortunately, this becomes weaker and weaker the more distance we travel. Just like when you're walking on a long walk, you get tired and tired, more tired and more tired, all right? So the intensity of that EPSP becomes weaker. Then it eventually will die off, okay? All right, so how do we make our EPSP stronger? Well, we can release more neurotransmitter, because if we release more neurotransmitter, we'll open up more channels, okay? So the more channels we open up, now we can maybe go from a -70 to a -65. Still not threshold value, but still, all right, we're onto something here, okay? Oh, I get it. If I open up 5 channels, not so much. But if I open up 10 channels, now I've went from -70 to -65. What happens if I open up 1,000 channels? Or 100 channels, right? And we get that. Okay, see where I'm going there? So sometimes, you know, it might take a couple neurons to stimulate that postsynaptic neuron to get it to generate an EPSP that's strong enough to reach that threshold value. Okay, that's what we're kind of moving towards. Our goal is to get to that negative threshold value. So we talked about the EPSPs, the excitatory. Let's talk about the IPSP, the inhibitory. Okay, the opposite effect. Okay, so this situation, when you see IPSP, the first thing you should be thinking of is hyperpolarization. Okay, my mother would kill me if she saw me writing. And again, it is a mouse, so I don't think I should be judged on my mouse writing skills. Okay, so a very similar type of situation, right, with IPSPs. Okay, you have these presynaptic neurons that are going to release their neurotransmitter. Okay, same story. So the neurotransmitter, okay, is going to diffuse across the synaptic cleft. In this case, it's going to affect chemically gated potassium channels or chloride channels. Okay, so what do we know about the chemically gated potassium channels? Well, when they open up, potassium diffuses and leaves the cell. Okay, and it takes its positive charge with it. So it makes the inside of the cell more negative. Or if we get our chloride channels to open up, chloride is in much more abundance outside the cell. So when those channels open up, chloride enters into the cell and it takes its negative charge with it, making the inside of the cell more negative. Okay? That's basically what we're going to see here. Now we're starting to make the inside of the cell more negative. So we could go from a negative 70 to negative 72. Okay? Same type of rules applies to IPSPs. Okay? They move parallel to the plasma membrane, but as they do, they are to experience resistance from the cytosol, just like the EPSP did. Just like when you threw your rock into the water, right? The ripples got weaker and smaller the further away from where you threw it in, right? And that's what will happen. So the longer or the further the distance is that this IPSP has to travel, it's going to become weaker and weaker, right? If it's strong enough to get to the 55 millivolt threshold, that's great, okay? But if it's not, nothing's going to happen. So that's what we see in this diagram here, okay? All right, same scenario. Postsynaptic neurons, they're going to release their inhibitory neurotransmitter into the synaptic cleft. It diffuses across. It can open up the potassium channels, causing potassium to leave, making the inside of the cell more negative. All right, or it can open up the chloride channels, allowing chloride to enter in, bringing its negative charge with it, making the inside of the cell more negative. Regardless, we're still going to get from a negative 70 to maybe negative 72, negative 73, negative 74, whatever. Okay? So the same rules apply. So we can see here in our graph, right? Everything's good. We get our stimulus. The gates open up. Potassium leaves or chloride enters in. And now the inside of the cell becomes a little bit more negative, right? Taking us further away from that threshold value. So the likelihood of us actually generating an action potential now becomes even harder, because we're moving away from that negative 55. Okay, that's not good. Well, it depends on what we're talking about here. All right, so this is where I wanted to talk to you about. All this stuff is going on. When I say at the same time, this can happen at the same time. So you can have excitatory, all right, presynaptic neuron, inhibitory presynaptic neurons. Both of them can be releasing their neurotransmitters, their excitatory and inhibitory neurotransmitters, onto that postsynaptic neuron. Okay? But it's just like anything. You have to tally up how many EPSPs are being generated, how many IPSPs are being generated, right? And they cancel each other out, one for one. Okay? They're always going to be fluctuating and trying to move, all right, that resting membrane potential either towards threshold or away from threshold. Okay? So what we're going to see is if the EPSPs outweigh or outnumber IPSPs and they get to the threshold of negative 55, then we'll get an action potential. Okay? But if the EPSPs are outnumbered, right, by the IPSPs, right, then we're not going to get an action potential. It will essentially have inhibited that neuron. So that's what we're seeing here in this picture here. Okay? We're seeing all these different, the red represents the IPSP presynaptic neurons, and then the green represents the EPSP postsynaptic or presynaptic neurons. Right? So they're all trying to manipulate the cell body here, all right, with the potential. But we add it up, see which one, has more, and if it's enough where the EPSPs make threshold, then we get an action potential. Okay? So how are EPSP graded potentials established in the receptive segment of the neuron? Okay, so we're going to deal with first excitatory neurotransmitters. Okay, they're going to bind on to the receptor in our chemically gated channel, right? Specifically the cation channels. It's going to be sodium and potassium. So granted, like I said before, even though that potassium is leaving the cell, right, it's not leaving the cell as much or as fast as sodium is entering into the cell. So you might have 1 molecule of potassium leaving, but you could have 10 molecules of sodium entering in. Okay, so it'll make it more positive on the inside. Okay, more positive. All right, so this brings me to, not bad. I was close, y'all. I was close. There's 99 slides in the slideshow. I did, my goal is always to do at least 33. 59 is not bad, All right, you got to hand it to me. But this is actually, I'm going to stop here because it's going to take me longer than the time that I want to. And plus, I've filled your brains up enough. I know it's a lot. And today's being Tuesday, so when you guys come back on Thursday, yeah, I know. But I can only strongly encourage you. I know I'm brain dead. May I be excused? My brain is full. I'm going to stop recording here. What I will